Oop, the last slideshow begins. The history of the Earth. I had thought that my plate tectonic slideshow would be the last one, but I realized that we have time for you to look at this, and you should. And I'll mention that to you in our Zoom class and by email. So, the history of the Earth, as depicted in this diagram, shows a spiral going back in time to the origin of the solar system 4.6 billion years ago, the ancestral explosion of some kind of supernova star that's reached the end of its life and exploded 6.6 billion years ago, and then the formation of our universe. Now, I don't know why they have 12 billion there. That doesn't seem right based on what I understand, but we will ignore that because I liked the spiral of the diagram, so I'm just going to say that this should be 13.7. And let's just go through how to read this. You have the Holocene epoch here. That's where we are now. Now, many of us believe that we should add a new epoch here called the Anthropocene, which would start in the 20th century. We have the Quaternary period, which is a period going back 1.6 million years, then the Tertiary, of which there is the Holocene, Pleistocene, Pliocene, Miocene, Oligocene. If we go back 35 million years, we still would find ourselves in what is called the Cenozoic era, but we would be in the Eocene. Then we could go back to the Paleocene, and then we would meet a border with a new era, the Mesozoic, middle life, Cenozoic, recent life. And if we traveled from 65 million years to 245 million years through the Tertiary, Cretaceous, Jurassic, and Triassic, we would have made it back to Paleozoic, the ancient life, which would include Permian, Pennsylvanian, Mississippian, and Devonian. That takes us back then to the last three. I don't know why I paused there. The Silurian, Ordovician, and Cambrian. And it is this marker, 545 million years ago, 550 million years ago, which separates the period on the Earth's history with complex life, with a fossil record, from that which came before, the Precambrian, which includes the Proterozoic and the Archean. This is another way to look at that. And again, we start at the Cambrian in terms of complex life and fossils, organisms that had either an exo or internal skeleton that could be mineralized and preserved in the rock record. Then we have the period of most of the Earth's history, 2.5 billion years. Actually, no, more than that. I don't know why I said that. 4 billion years that include the Proterozoic and the Archean, with the Earth forming 4.6 billion. And one of the themes of this particular slideshow has to be that rocks tell stories, or rocks, especially sedimentary rocks, can unravel the complexities of life. And the reason I say especially sedimentary rocks is because in this period, since the evolution of exo and then internal skeletons, we've been able to unravel this complexity through fossil discoveries. What can rocks tell us? The environment in which they were formed, organisms that lived in the environment, events that led to the development of the environment, the succession of events, which came first, second, third, fourth. Then the actual age of rocks. Two types of dating determining the age of a rock would be relative dating, where you can simply say what is older or younger to units of rock compared to formations, or absolute dating, where you use radioactive elements and their instability as a clock, and you can get a number for the age of the rock. Relative dating, well, rocks are placed in their proper sequence of formation, which formed first, second, third, etc. Relative dating cannot tell us the exact age of the rock, but rather the event that came first, second, third. The first principle of relative dating is the law, or first law of of relative dating, the law of original horizontality. Sediments that are deposited in water form in flat, level layers parallel to the Earth's surface. This allows us to say that the bottommost layer of horizontally bedded rocks will be the oldest. And that takes us to the principle of superposition. Bottom layers of series of sedimentary rocks are always older than the layers above. The principle of superposition. Of course, we have learned through plate tectonics that this pile of horizontal rocks could be folded, thus making it difficult to determine which is the oldest layer and which is the youngest. But if the layer has not been folded, the principle of superposition holds true. Here's an example of how the law can be tricky. Forces within the earth can tilt, fold, and overturn rocks so that in some cases the younger layer is found under the older. So here would be the flat-laying rock. Tectonic forces at either end of this horizontal layering are pressing against the rock, deforming it, folding it, until you get to the point where you've actually turned over part of the rock. And so now you want to know what's the oldest and what's the youngest, and it begins to get a little tricky. So you need to know that tectonic forces can play with the principle of superposition. The principle of cross-cutting relationships. In this principle, sometimes faults, where rocks sliding down against each other. So here would be a fault, a normal fault, where the right side is slipped down in relation to the left side. Sometimes the fault or magma intrusions. Here would be an igneous intrusion into beds of sedimentary rock. The igneous intrusion melting like the Palisades cliffs across the George Washington, across the Hudson River. Sometimes the faults or magma intrusions are younger than the rock strata already in place. So if we were going to age by letter this pile of rocks, we would say that C is the oldest, followed by B, followed by A, at which point A is eroding and all three of those layers are intruded by D. So C to B to A to D to the fault E. That's the last thing that happens on this diagram. The right side slips down. We know it's the last thing because this was already in place by the time it slipped. Unconformities between strata. They represent major geological changes in the Earth's history, such as a change in climate or sea level, or a break between a period of tilting and folding and more normal deposition. They are breaks in the sequence and layers of rocks and thus time. An example, layers of sedimentary rocks are usually deposited in a marine settings in unbroken sequences. But rocks show that sometimes deposition stops and erosion takes over. Why would that be? Well, the layers are uplifted by tectonic forces. They're lifted up above sea level during the convergence of plates, and they then are worn away by weathering of the rocks, erosion, which is moving the sediments away, and those sediments can be deposited in a marine environment far away. New sediment, again, is deposited on eroded layers as sea level rises. New rocks form. This is a disconformity. There are three types. That's one of three types of unconformity. So a disconformity is one of three types of unconformities. Three types. Angular, rock layers that are tilted and eroded and new layers deposited horizontally above the tilted layer. Disconformity, irregular erosional surfaces between parallel layers, difficult to pick out, difficult to identify. Nonconformity, sedimentary layers are on top of igneous or metamorphic layers. So here you have your disconformity. You had some kind of shale to, say, a siltstone, to maybe this is a sandstone, and then the sandstone is above sea level and it gets eroded, and then sea level rises and deposits a limestone and another shale. Or shale I'm not sure what this is supposed to be. Let's just say siltstone. I'm not sure, shale, some kind of sedimentary rock sequence here. It's a little bit hard to read what they want these different colors to be. But this is definitely typically a shale or a siltstone. We'll call this a mudstone. Then a limestone, normally deposited in flat layers just like this. In this case, they got tilted. They're tilted and lifted above the surface of the sea, eroded, then sea level rises, and you get new layers. Angular unconformity. They're unconformable. They're the sequence of rocks has been broken. That and this line here is the unconformity, the break in time. Or flat lying, minding own business when suddenly igneous rock intrudes, melts its way through the sediment. So if this got eroded, say to this layer, you would see this igneous rock above, say, this shale. Here's the development of an angular unconformity. So deposition of rocks A, B, and C. Then the uplifting of the rocks, the tilting, and the erosion of A, B, and C. Then the subsidence, sinking down as sea level goes up. Right? Now below sea level, the rock layers and new layers, F and G, deposited above, unconformable in relation to A, B, and C. There's an angular unconformity. These are standing straight up. This is sitting on it virtually horizontally. This is one of the more famous rock formations on Earth. I didn't move it over. My head is here, but I think you can see it. The development of a disconformity. Here we have the deposition of layer 1, 2, 3, and 4. Then uplifted and above sea level, eroded, and then sea level is higher, and now the erosion surface is covered by sandstone and limestone under the water. Disconformity in a rock. So this would be the disconformity. We had this deposition of A and B. We had erosion along the surface. And then we had additional deposition at E and F above it. A disconformity here, represented with a curvy line on a cross section. So, and this diagram is called a cross section, right? This curvy line shows that first we had flat-lying sandstone, then a flat-lying conglomerate, then a flat-lying shale, then a flat-lying limestone, then a flat-lying shale, and they got folded, eroded above sea level, and then sea level rises, limestone is deposited, and another shale. Disconformity. Development of a nonconformity. In this case, we have deposition of rocks J and K, metamorphism of rock IM, right? Uplift, J and K disappear, IM is left behind. Nonconformity because sea level goes up and a limestone and then a shale are deposited on top, P and Q. Here would be an example of a nonconformity, the Grand Canyon. This is underlying metamorphic rock, 1.7 billion years old at the Grand Canyon. Then a break in time of 1.2 billion years when then sea level covers the metamorphic rock and begins to deposit the new layers of sedimentary rock. So this is a huge break in time. So we have the Tapeats sandstone, 550 million years old, above the Vishnu schist, which is 1,700 million years, 1.7 billion years old. So a nonconformity of 1.2 billion years. That's a huge nonconformity. Now, if you want to learn about the rocks on Earth between this point and this point in the history, you can't go to the Grand Canyon. You have to go somewhere else. That's one of the things about the history of the Earth that's so fascinating and has really allowed the history to get filled in, because over the last 150 years ago, people have spent so much productive time mapping the geological formations and finding connections in different parts of the world. And when they have a huge absence of 1.2 billion years, they go and look elsewhere to fill in the rock record, to fill in what was happening on Earth between Vishnu schist and Tapeats sandstone. How can rocks and geological events in one place be matched with those in the other locations? Well, that's what we were just talking about in a way. You correlate. You determine that the rock layers in different areas are the same age. You walk the outcrop. You physically trace the layers from one place to another. You match physical characteristics. Color, composition, thickness, fossil remains, how it's tilted, how it's dipping over a large area. The index fossil, remains of organisms with distinct body features that were abundant and had a broad but short existence. So, I'll give you an example of that in a minute. Key beds, well-defined, easy to identify layers of formation, i.e. volcanic ash. So let's say you were in 1860 when Krakatoa, a huge volcano, exploded and sediment from it was deposited over large parts of the earth. Well, if in 1 million years or 2 million years or 100 million years, there'll be a layer of ash in the rock record that will tell of that event. So, let's go back to index fossils. They're very important. An index fossil is a fossil in the rock record that is characteristic of a particular geologic time or environment. So, a mastodont, or beluga whale for recent past, or a elliptocephala, which is a type of trilobite from the Cambrian period, or a Cooksonia, a type of plant, perhaps from the Devonian period. The condor, recent. We have a dinosaur, Coleophysis, from perhaps the Cretaceous period. So we have a bunch of fossils that have been found only in those particular time periods. And so you can use them as an index the same way you would use an index in a book. I want to find a particular thing. I go to the index. The organism, the fossil in this case, is that index entry. That was the word I was looking for. So on your reference table, you've got a list of index fossils that are useful in New York State from A to Z. Well, not just New York State, from A to Z. And you can see what we've done here. Time distribution of fossils, including important fossils of New York, but not only. And it says the center of each letter circle indicates the approximate time of existence of a specific index fossil. E.g., fossil A lived at the end of the early Cambrian. So that would be here. Elliptocephala. At A, you go to the left. It lived in the early, that's the epoch, Cambrian. That's the period of the Paleozoic. Or you go to Dicelograptus, K. Well, K, and by the way, A is a trilobite. It tells you here that that's the kind of critter. K is a graptolite. Graptolites existed from the late Cambrian, it looks like, up until the Pennsylvanian, when they seem to have gone extinct. And K, of that group of species, or that genus known as graptolites, that existed in the late Ordovician. It's an index for that period. If you find that fossil, it is from the late Ordovician. If you find A, it is from the early Cambrian. If you find L, it is from the late Triassic. And what is L? L is Coleophysis. If you find, let's want to find one a little bit higher up. Well, we'll do J. If you find J, it's from the border between or late Cambrian, early Ordovician. So this is the way in which we use index fossils. Each of these fossils is unique to an epoch of a certain broad time in the past and a period. And remember, these periods are not absolute in these dates. It's not exactly necessarily, although they have been probably correlated to radioactive dating. So we can say that the Cambrian is 542 million to 488 when the Ordovician starts, to 444 to 416 to 359. And then they divide it in some cases into this early, middle, and late, but not all, because maybe in the Pennsylvanian we don't have enough information. Another thing about this reference table is that you'll notice the New York rock record, what rocks can be found, therefore what fossils are potentially found in New York, is not complete. We have a lot of Cambrian Ordovician, Silurian, Devonian, only a little bit of Mississippian, a little bit of Pennsylvanian, and then we have no Permian in New York. Very little Triassic, very little Jurassic, and then not much Cretaceous. No Paleogene, no Neogene. And going deeper, we don't have much in this middle and early Proterozoic. So this is a useful page, page 8 and 9, in terms of determining the age of the Earth using index fossils, the age of a rock using index fossils. Now we would have here, well, we would want to list this from oldest to youngest. This is a block diagram, and we have, it's a little hard to see, we have A, B, C, D, E, F, and G. We have Y, which looks like a fault. We have X, which looks like an unconformity. We have J, which looks like extrusive lava. We have H, which is an intrusion, and then this uplifted laccolith. We have I, which is an intrusion. So we'd have to then figure out what came first. And here telling you that we have shale, limestone, sandstone, and igneous rock with the pluses and the V's. Well, logically, we would want to think that the first layer that existed in this block diagram would be letter G. And letter G is older than F, and F has slid down in some faulting here. So we probably had G, and then F, and then E, and then did we have D? Well, perhaps. It looks like it. Then, well, this clearly melted in to this, so that might have been the next thing. Then this must have been all uplifted and all eroded away. So all this is eroded away. And then looks like we must have had the faulting. So all this slides down. Though it may have slid down before the intrusion. And in fact, I think that's probably true. So the faulting comes before the intrusion. Then sea level rises and we get a sandstone and a limestone and a shale. And we get two intrusions, H into the shale, but not above the surface, and this one over here, up and out with J. So, looks like it goes G, F, E, D, Y, I, C, B, A, H, J. I forgot X. X after D. So you can confirm that yourself. Absolute dating, the next type of dating. Absolute dating tells us the actual age of the rock. Absolute dating uses radioactive decay to determine the age of a rock. Absolute dating, finding the actual age. Review of atoms and isotopes. All elements are made up of atoms. The nucleus has protons and neutrons in it. Nucleus has the most mass. Surrounding nucleus, electrons in the electron cloud of uncertainty. Atomic number. Each element has its own atomic number based on the number of protons. Atomic mass. The number of protons plus the number of neutrons, which is not always the same. The same element will have the same number of protons, but can have different numbers of neutrons, and these different forms of the same element are called isotopes. Isotopes can be unstable or otherwise known as radioactive. It can also, of course, be stable. They exist, but the number of neutrons in the relation to protons allows the nucleus to lose particles in a process called radioactive decay. Radioactive decay, the parent material decays into the daughter material, or the child, in a predictable manner. And here we would have an age of something. Something that is relatively new, a freshly cooled piece of igneous rock. It has radioactive material in it. We can say that one half-life of that rock, radioactive material, has gone by when the proportion between the parent isotope and the daughter product has changed by one half. Then, if one half again changes, we have gone through 2 half-lives. And what scientists have discovered is that you can put a time on how long a single half-life of a particular radioactive element takes. So this is called the alpha decay of uranium-238 nucleus. It's hard to really see, but what happens is U-238 is the common form of uranium. It's radioactive. It decays. It emits proton, in this case 2 of them, neutron, in this case 2 of them, which is equivalent to a helium atom. And that decay creates a new element, thorium-234. An alpha particle, in this case, that's this, is a helium atom. And that's what's happening with uranium all the time. And if we took uranium and went through the entire sequence of radioactive decay that is occurring with this element, we would see that at first there would be this decay to thorium, which would take a certain amount of time, followed by the decay to Pa, I'm not sure what that is, I can't remember, to another isotope of uranium, to thorium of another isotope, to radon of an isotope, to radium and radon, I think that's it, polonium, lead, bismuth, not sure, lead, mercury, not sure, and finally, the first one of all of these steps that has a stable isotope would be lead 206, and it would have taken 4.46 times 10 to the 9th years for that full event to take place. And it's telling you in each one of these examples how long they last. The thorium here lasts 24 days. The Pa lasts 6.7 hours. The uranium-234 lasts 245,000 years. The thorium, 75,000 years. The radium or radon, 1,600 years. The radium or radon, 3.8 days, and so on and so forth. And likewise, it's telling you what's coming out. In this case, alpha particles, negative beta, alpha, negative beta, negative beta, negative beta. And that change, that slight change, finally brings us to lead, 206, the stable form. And again, here is what alpha radiation is, 2 protons and 2 neutrons. Here's beta, it's a negative electron. The positron, a positive. And the gamma radiation, which are photons of electromagnetic energy. All of these forms of a radioactive decay are potentially dangerous. So half-life is based on a simple proportion. Half-life is the time it takes for 1/2 of that original isotope to turn into a new stable isotope. And here, that amount of time for uranium is 4.468 times 10 to the 9th years. 4.5 billion years, just about the age of the Earth. This number never changes with radioactive decay because radioactive decay is not dependent on temperature or pressure or any basic physical parameters that might change it on the surface or near the surface or deep within the Earth. So the decay continues. It's a clock. It's a most effective clock. So if you started with a radioactive isotope in a rock and you had 100% of that, right? One half-life would be when half of that radioactive isotope in the rock had decayed. That would be one half-life. That would be a certain amount of time. Then the half would decay into a quarter. That would be the second half-life. 25% would remain of the original. Then the quarter would split into an eighth. 12.5% of the original would remain, which would split into 1/16, 6.25% of the original, and so on, until you can't actually detect what's left, and thus we would say you have a limited number of useful half-lives, which is really only relevant with carbon. So these are the radioactive isotopes that are used often in earth science. This is on the front page of the reference table, the top left. Carbon-14 is a very common radioactive isotope used for living things that were once alive, because there is a unstable isotope of carbon in all of us all the time that decays to a stable form of nitrogen. One half-life of that carbon that is radioactive decaying takes 5,700 years. In contrast, potassium-40, which is found throughout the Earth down towards the core, decays from the unstable isotope of potassium-40 into both 40 argon and 40 calcium, and that half-life takes 1.3 billion years. Then, as we just said, uranium can decay to 206, lead, the stable form of lead, and again, these are the stable forms of argon and calcium, in 4.5 times 10 to the 9th billion years. Rubidium is useful in some cases, but look at its half-life. It decays from rubidium-87 to strontium-87 in 4.9 times 10 to the 10th billion years. 49 billion, older than the universe, it takes for one half-life of that element that is radioactive to decay. If the half-life of an isotope is known, the age of the rock can be determined by figuring out the amount of parent in relation to the amount of daughter. Every half-life, the percent of the daughter product will increase predictably in relation to that of the isotope, which decreases. Carbon-14 is special because C14 is used to date the remains of living things. All living things contain carbon, and while organisms are alive, the amount of C14 remains constant. Any decay is replaced. When an organism dies, the CO14 decays and is not replaced. The longer the organism is dead, the less C14 in the organisms remains. So that would be in the organism's bones that were left behind on the surface of the Earth. C14 again has a short half-life. After about 50,000 years, there's not enough of the original radioactive isotope to use to date the rock. Why do we use these radioactive isotopes? Because they're constant, predictable, not affected by moderate changes in temperature or pressure, and therefore reliable. Rocks that are metamorphosed or under high heat and pressure do have their clocks restarted. Now, let's try to do this little problem. You are rummaging in your family's old trunks. You find an old bone. It contains 50 grams of C14 and 50 grams of N14. How many half-lives has it undergone, and how old is the bone? Well, it's got an equal amount of C14 and N14, so that would mean 50%, one half-life has gone on, and the half-life of carbon being 5,700 years would mean that one half-life has occurred for that bone. That bone is 5,700 years old. If the bone contains 25 grams of C14 and 75 grams of N14, how many half-lives? Well, another half-life has taken place. We have reduced the 50 grams of C14 and changed it. It has transformed itself through radioactive decay into 25 more grams of N14, or a total of 75. Therefore, 2 half-lives have gone on, 11,400 years. What percentage of C14 is left after 5 half-lives? Well, you just keep dividing. It would be 3.125%. What happens to the amount of N14 as the C14 decays? It increases. And there we have our way of dating the planet. Because of radioactive isotopes, we can go beyond the relative dating of fossils in particular types of sedimentary rock units, and we can move to the Precambrian, the Proterozoic, and the Archean, and date based on what are reliably found radioactive elements in the rock. Let's now finally just go through the geologic time scale. There are 3 eons. I always get this stuff wrong, but you have the reference table, so you just look there. The Archean, 4.6 to 2.5 billion. The Proterozoic, 2.5 to 600 million years, together referred to as the Precambrian. And we can break both of these into early, middle, and late. The Phanerozoic, 600 million to the present. Cambrian is the first period of the Phanerozoic. Eras. Within the Phanerozoic, there are 3 eras. Paleozoic, old life, marine invertebrates, earliest land plants and animals, insects. Mesozoic, middle life, reptiles, early mammals, birds. Cenozoic, recent life, mammals dominate, flowering plants dominate, grasses. Within each era there are periods, so determined by rock type and index fossils. Oldest period, the Cambrian, named for a region of Wales where it was first distinguished as a unique period. Most recent periods are the Paleogene, Neogene, and Quaternary. The Quaternary is the current period, and it followed the Tertiary, a term no longer used. Within each period are epochs. For most periods, these are early, middle, and late. In the Cenozoic era, there are epochs: Paleocene, Eocene, Oligocene, Miocene, Pliocene, Pleistocene, and the current, which is ending and going to the Anthropocene, the Holocene. On pages 8 and 9 of the ESRT, review the rest of the geological history of the New York State. Columns from right to left on the life on Earth, the New York rock record, the time distribution of fossils, important geological events in New York State, and inferred positions of Earth's land masses. And with that, I'll just go back to show you those. So again, life on Earth, the New York rock record, the time distribution of fossils, important geological events in New York, such as the advance and retreat of the last continental ice glaciers, sands and clays of the Cretaceous underlying Long Island and Staten Island deposited on the margin of the Atlantic Ocean. Dome-like uplift of the Adirondack Mountains begins in the early Cretaceous. And then here we see the inferred positions based on plate tectonics of where our continent might have been going back to 458 million years ago. And with that, I will say goodbye.